So again, welcome to Math 123 Tuesday night, 8 to 9 p.m. And we are looking at section 3 today. And just a reminder one more time, the assignment orientation, web work 1 and 2, and the discussion board 1 are all due tomorrow, Wednesday, January 23rd. And then web work number 3 and quiz 1 are due on January 30th, so next Wednesday. So here's what we're going to do. We're going to look at section 3, which starts on page 24 for us. On page 23, there's a table there to fill in. It has the number of zeros and the powers of 10 and the names of numbers. And we're going to start off with page 24, looking at using powers of 10 and scientific notation. So it says here, writing out large numbers is cumbersome. This is where scientific notation comes in. And here's the procedure for writing a number in scientific notation. It says move the decimal so that there is one non-zero number in front of or to the left of the decimal. And then it says write this number times the corresponding power of 10. So in the example here, the number 12,000, the decimal point, if a decimal point's not written in the number, it's at the right-hand side. So we move the decimal 1, 2, 3, 4 places to the left to get one non-zero digit to the left of the decimal only, and it becomes 1.2. And since we move the decimal 4 to the left, we're going to put a power of 4. If we move the decimal to the right, we actually subtract 1 on the power of 10 each time we move. So when you move to the left, you're adding 1 to the power each time you move, and when you move to the right, you're subtracting 1 from the power each time you move. So if we look at the next ones here, it says write these in scientific notation. And so we can see this and go, okay, 3, the decimal point is going to go right there. So there's one non-zero digit to the left of the decimal. And we would have 3.257 times 10. Okay, I have a new mouse, and so it's a little bit crazy right now. It's super sensitive. My other mouse died. So we want to know how many places did we move the decimal? And it looks like you are agreed that it's 8. And so we would put an 8 as a superscript there. So 3.257 times 10 to the 8th. And then number 2 says 7.3 billion. And this question is a little bit different because it doesn't have the number written out. And we can refer to the chart on page 23 and 1 billion. 10 to the 9th. So when we see billion, we can write the number 7.3 times 10 to the 9th. Okay, I'm going to try and plug my old mouse back in and see if I can get it to work real quick. All right, this mouse moves much slower and I can have a little bit more control of it. All right, good. So the next one, number 3, says 92.96 million. So I'm going to do the same idea on this one, and I'm going to ask you a question. 92.96 million is times 10 to the 6th times 10 to the 6th. And the problem here is, and some of you have it already, that this is not actually in scientific notation correctly. We have to move the decimal 1 more place to the left, so it becomes 9.296 times 10 to the 7th. So note, just because it has million in the word part of that number, that doesn't mean that our final answer is going to be 10 to the 6th. So we put it as 10 to the 6th and then change the decimal 1 place to the left to make only one non-zero digit be to the left of the decimal. So number 4, 0.86 million, so I'm going to try this one the same way. So 0.86 million again is 10 to the 6th. And there is a problem, and some of you have identified it. We have to move the decimal to the right one to get there to be one non-zero digit. And remember, when we move the decimal to the right, we subtract 1 from the exponent, and since it's already a 6, we're going to make it a 5. Okay, you guys are awesome. I see most of your answers in here look fabulous before I even had a chance to explain it. That's awesome. Very nice. So that's how we write numbers in scientific notation if they're not already. And what we're going to do next is, it says use a scientific calculator to perform the following calculations. So what I want to show you about these two calculations, one's a multiply, one's a divide, is when you multiply, you add the exponents. When you divide, you subtract the exponents. The first minus the second, or the top minus the bottom, if they're written as a fraction. So what we do is we handle the number part first. I'm going to grab my calculator here, and I'm going to toss this in there. So I'm going to take 5.92 times 6.3. And here's what I got. I got 37.296. Now, there's a couple of things here. So times 10 to the, since we're multiplying, we're going to add the exponents. So 9 plus 5 is 14. And there are two things on this that we want to make sure that we understand. So one of them is that it's not in scientific notation because there are two numbers to the left of the decimal. And the second thing is that when we're multiplying and dividing in scientific notation, we have to in our answer have only the number, excuse me, let me say that again. The number of digits in our answer has to match the least number of significant digits in the problem. And so if we look at those two numbers, 5.92 and 6.3, the least number of significant digits is the 6.3. There are only 2 digits there. So our answer can only have 2 digits in it. So I'm going to move the decimal to the left 1 and make it 3.7. Since the 2 is less than 5, the 7 doesn't round. Times 10, and since I move to the left 1, it becomes 10 to the 15th. So that's how we would write our answer. We want to have the least number of significant digits that's in the problem. That's how many significant digits should be in our answer, and that's for multiplying and dividing. When we add and subtract, the way we figure out how many digits go in our answer is the least precise number. So, if you're adding tenths and thousandths, the tenths place is the least precise, so you should have only the tenths place in your, or the tenths place should be the last place in your answer. So adding and subtracting, it's the least precise number, but multiplying and dividing, it's the number of digits in there. So on number 8, we have 2 digits, or 2 significant digits or figures, and 3, and so our answer is only going to have 2. Now when we divide this one, we're going to do 1.9 divided by 4.62. So 1.9 divided by 4.62. And on my calculator, I got 0.411. And there are some other digits after that, but they don't matter because we only need 2 digits. And this 1 tells us that the first one stays the same. So this is times 10, and we're going to subtract the exponents this time. Looks like 13 minus 4 is 9. And then we have to move the decimal one place to the right to get it to be in correct scientific notation, 4.1. And since we moved it to the right, we're going to subtract 1 from the exponent, and it becomes 8. So 4.1 times 10 to the 8th. No, if you use your calculator on your computer, that's fine. All right, so 4.1 times 10 to the 8th. So what I want you to do is I want you to try the next two, like try those. Actually, the next, let's do this. Actually, let's make this our group activity. So I'm going to separate you into rooms, and they're like virtual rooms. And room A is going to do number 10. Room B is going to do number 11. Room C is going to be number 12, and room D is going to be number 13. And I don't think these are on the page that's listed there, 233. I don't even know if they're on a page in your book. Oh, they're on page 20. I don't know where they are. They might be on page 233. Let me look. They are on page 233. I don't know why I didn't think they were for a second here. So yeah, so find page 233 in your book. And we'll see. Kiara, I'm not sure how this will work, but if it works, great. Then don't worry about it. I know you're in here. I know you're paying attention. Okay. So these are on page 233. Again, room A is going to do number 10. Room B is going to do number 11. Room C is going to do number 12, and room D is going to do number 13. So let me separate us. And again, remember there's going to be a tab that shows up, or your screen's automatically going to get you in there. I got you, Pamela. And so let's see here. All right, so it's putting in your rooms now. All right, so Pamela, Kiara, and Carly, or Pamela and Kiara, if you can hear me, you might in your screens, like if you're on your phone and you're viewing this, you know how on your on your, uh, you can see all the different tabs in that are online in your browser. See if a new tab popped up in the back there, and that might get you in. All right, Group B, can you guys hear me okay? All right, and I want you to notice that it looks like you found it. Everybody found the little chat box that goes with our room here. Excellent. And then I see that there's an answer already in there from Kelly, but I want you guys to introduce yourselves to each other. Take a minute to do that and see if you agree on that answer, okay? And I'll be back. All right, breakout B. Hopefully you got an answer for number 11. I want to let you know, I'm giving you like a 2-minute warning, 1.5 minute warning. I'm going to bring everybody back together in about 1.5 minutes or so. And just wanted to see if you were able to get an answer and talk to each other and meet each other. Did you come up with an answer? Oh, okay. Okay, well, give me your thoughts here. We've got about a minute before I bring everybody back, so talk to me. Well, the question you have to ask yourself, since we are multiplying, is how many significant digits are there in each of the two pieces of the problem? So it's not about the place value, it's about how many digits there are. There are 3. So your answer should have 3 digits in it. Oh, I don't think it's 1.70. So you don't want to round, you want to round the third digit is the one you would round. So 1.69, yes. And it is times 10 to the 11th. Yep, 1.69. So 3 digits, you don't want to round it until you're just rounding the third digit. And since the number after the 9 is less than 5, you keep the 9. All right, bring everybody back in about 1 minute. Okay, so I think we're all back. All right, so Kayla, I know you asked me a question, and the answer is no, I don't. I don't hear it. Okay, so let's see. So letter A has 2 significant digits here. And so when we multiply, we're doing 3.8 times 5.7, and that's 21.66. So since there are only 2 digits, we're gonna move the decimal 1, and we're gonna change this 1 into a 2 because we're gonna round it up. So it's gonna become 2.2 times 10 to the, it would have been 13, but it becomes 14 because we had to move the decimal 1 to the left. Okay, number 11, 3.28 times 5.16, when we multiply those, we get 16.9248. But we only have 3 digits in each one, so we only want 3 digits in our answer. So we're going with the 16.9 to start, times 10. We're going to add the exponents. 7 plus 3 is 10. It's not quite in the scientific notation yet. We have to move this decimal. So there's only one number to the left of the decimal point, so it becomes 1.69 times 10 to the 11th power. Did that help, Roberta? Oh, perfect. And group C had number 12. Dividing these, when I divided them, I got 0.2911. There are only 2 significant digits in each of those numbers, so it's really 0.29. We're going to subtract the exponents, so 7 minus 3 is 4. And then we have to move the decimal 1 to the right to make this in proper scientific notation 2.9 times 10. And so since we moved to the right one place, we subtract 1 from the power and it becomes a 3. And then letter D, or group D, I didn't get to check your answer, but number 13, we're dividing 4.31 by 6.21. And when we do that, we get 0.6940 and then some other digits. 3 digits in the problem, so we need 3 digits in our answer. So we're going to cut it off right there. The 0 does not make the 4 turn into a 5. So to start, we have 0.694 times 10 to that. We're going to subtract the powers. 11 minus 4 is 7. And then we have to put it in proper scientific notation, just like you did, Kendra, and make it 6.94 times 10. And since we're moving the decimal again, one place to the right, we're going to subtract 1 from the power, it becomes a 6. So 6.94 times 10 to the 6th. So as our operations with scientific notation, it took a little bit longer than I wanted it to. Okay, you guys, everybody got in the rooms okay, and in the breakout room, except the 2 that are on the phone, that was expected. And so let's go ahead and we have just a little bit more to do. We have to talk about per capita and proportions, okay? So I'm trying to do this quickly. Per capita is on page 26. So this is going to go a little bit faster. I'm just making you aware of that. So this says consider the ratio of Skittles to the United States population. If 200 million Skittles are produced each day and the U.S. population is approximately 324 million, the ratio of Skittles to people, or Skittles per capita, would be calculated as shown below. So per capita means per person. That's what we're doing. So Skittles per person, 200 divided by 324 would be 0.62 Skittles per person. And so let's look at number 1. It says, if there are 400 million M&Ms produced each day, find the number of M&Ms produced daily per capita using the same population as above, and then write your answer in a meaningful sentence. So this time we're going to take 400 million. We don't have to put the millions on because they are both in millions already and they would cancel out. The units would. So 400 divided by 324, I got 1.23, and it would be M&Ms per capita. And that means each person would get 1.23 M&Ms if we distributed them evenly or equally. So we want to write it says write your answer in a meaningful sentence. And so my meaningful sentence, I'm just going to say it. My meaningful sentence would be something like, if the daily production of M&Ms were evenly distributed among all Americans, each person would get 1.23 M&M candies. So that would be a meaningful sentence. And you could have some variation of that, but it's about evenly distributing them among the people. So if everybody got the same amount, then there would be 1.23 M&Ms per person. That's what we're doing for our meaningful sentence. So number 2 says, the National Center for Education Statistics, NCES, says that the state of Indiana spent $9.97 billion on K-12 students in 2014-15 school year. If there were 1.05 million K-12 students in Indiana that school year, find the amount spent per student. And it says when working with such large values, it may be helpful, it may be useful to use scientific notation. And so what they're talking about here is using a scientific notation. So we're doing dollars per student, 9.97, and this is billion, so it's times 10 to the 9th. Per means divide by the number of students. 1.05 million is times 10 to the 6th. And then you can actually just do this on your calculator. Since we're dealing with dollars, we want to have dollars and cents for our answer. So we can take this out to the nearest penny. I see some of you. Oh, look, Kelsey, looks like you got it there. And Kaylee, out to the nearest penny. That looks great. So it is dollars per student. So it's going to be $9,495.24. And you could actually write these numbers out. So if you wrote them out, this would be 9970, and then 0000000 divided by 1050000. So if you did it in your calculator like that, you would get the same result. So, and if we put it in the scientific notation, we do get what you have there, Kaylee, and then we would want to take it out of scientific notation. So that means move the decimal 3 places. So you'd have it after the 5, and it does make 9495.24 per student in this case. All right, so next thing it says here is we're looking at Illinois, and they spent 28.54 billion and had 2.05 million students. So let's find the amount they spent per capita. $28.54 times 10 to the 9th divided by 2.05 times 10 to the 6th. And same idea, we want to get dollars and cents. So it looks like some of you have answers in the chat box, 13,921 and 95 cents. That is what I got. It's $13,921 and 95 cents per student. And again, that's if they evenly distribute the funds, per student. And generally they don't. So it says compare your answers above using a few meaningful sentences. And so I did this 2 ways. One way is I looked at the difference between these 2 values, and it's about $4,000 difference. So one sentence you could write is something like Illinois spent about $4,000 more per student than Indiana in the 2014-15 school year. Let me say that again. Illinois spent about $4,000 more per student than Indiana did in the 2014-2015 school year. So it would be one meaningful sentence. Another one, because it says a few, so I'll give you another one. So $4,000, look at this. This is $9,495. I'm just going to say that's about $10,000. And 4,000 out of 10,000, let's see, 4,000, I don't want to say it like that. Let me look at it a different way. I'm going to say this is about 14,000. And that $4,000 is actually about $4,500, which is about 25.25. So we could say that Illinois spent about 25% more per student compared to Indiana. So we could bring it further and do a part to whole or something like that. The part that was different was the 4,500 to the whole 14,000 in Illinois. And we could say that Illinois spent about 25% more per student than Indiana did in K-12 from 2014-15 school year. So just because it asks for a few sentences. All right. So I do have to speed this up a tad bit because I've got all that to do still. Let's see. To make sure you guys have a good sample of what your homework is going to be like. So what I'm going to do is I'm going to show you how to do the US and fill in the numbers, and I'll just put in the rest of the numbers so we can answer the questions. So an important thing to look at here is that this says in millions. So if we're going to look at this comparison, so where it says calculate the licensed Starbucks locations per capita. And then it says write the per capita values in scientific notation in the table. So what we're going to do is we're going to take 6530, that's the actual number of stores, and divide it by the population. Now the population is 325,700,000, so 0.7. This is times 10 to the 6th because it's the number of millions. And when we divide that, we get, just like you guys have in the chat box, 0 point, and there are 4 zeros, and then 2, and I'm going to bring it out to 0, 0. So we have enough decimal places for all the other answers, so we can compare them. So it says Starbucks per capita in scientific notation, 2.00 times 10. Since we're moving the decimal to the right, 1, 2, 3, 4, 5 places, it's going to be the negative 5th power in scientific notation. Then it says the Starbucks per 100,000. So now what we're going to do is we're going to take that answer and we're going to do one of two things. We're either going to take this original answer and multiply it by 100,000, or we can take it and move the decimal 5 places. We can actually, let's look at the scientific notation. So one way is to take that and multiply it by 100,000. Another way is to take this, and if we're multiplying by 100,000, we would move the decimal 5 places because there's 5 zeros to the left, or add 5 to the exponent is another way to think about it. So if we add 5 to the exponent, it becomes 2. Or if you multiply it by 100,000, you get 2. Either way. So let me put the numbers in here for China, and you help me out with these right 2 blocks, and I'll just fill the rest in. So when I divided China's numbers, I got 0 point, and I got 5 zeros, and then 208. So if we're going to write that in scientific notation, it's going to become 2.08. I want to know what power it would be. And it looks like Kelsey has an answer in there. Ashley, Kaylee, good. Yep, -6. And again, I'm using 3 significant digits here because I want to be able to compare them. So if I multiply that by 100,000, I'm going to get 0.208. So it looks like the US is 10 times as many per capita as China. And then this one is 1.44 times 10 to the negative 5th. So 1.44 per 100,000 people. 6.12 times 10 to the negative 6. So 0.612 per 100,000 people. So it says use the number of Starbucks per capita for the United States in a meaningful sentence. The Starbucks per capita, so that's this one for the US. Use that in a meaningful sentence. We would say we have to look at the data a little bit more. So this, in the book, it says it's from 2017. We would say something like, in the US, there were about 0.00002 Starbucks per person or per capita in the United States. And I see that you're doing it per 100,000, and it makes more sense if we do that. But since this says per capita, we want the 0.00002 in our sentence. And then number 7 says, let's use the per 100,000 in a sentence. So now we wouldn't say per capita, we would say, in South Korea, there were about 0.612 Starbucks for every 100,000 people. in 2017, or in 2017, Korea had about 0.6 Starbucks per 100,000 people. That would be our meaningful sentence. All right, and then lastly, let us look at proportions. So now I'm flipping over to page 31. Really 31 and 32. And we'll see what we can do here. So proportions, the way we look at proportions, there's a few different approaches. And this example here says, I want you to notice it starts with Lafayette to Vincennes. Oh, let me do this different. Inches to miles, Lafayette to Vincennes. This is Lafayette to Fort Wayne, and it's still inches to miles. Notice how the units are inches are across, miles are across. Lafayette to Vincennes is straight down, Lafayette to Fort Wayne is straight down. So these are about organization. If we look at this one, now it has inches to inches, and it has Lafayette to Fort Wayne, Lafayette to Vincennes. Notice, to keep things consistent, we have to have Lafayette to Fort Wayne across from the other one in Lafayette to Vincennes. These are miles and miles. So in the top example, the units go across, the cities go down, corresponding city. In the second example, the corresponding cities go across and the units go down. So it's about matching those things up. The same result, though, occurs because when you solve a proportion, we do this by cross-multiplying, multiply the two numbers that are diagonal from each other, and then divide by the extra number. So we're multiplying 4.5 times 160. Same thing in this case. It's still 4.5 times 160, and then divided by 6. So let's see what that comes out to be. Looks like you already have it in there. Gosh, you guys are awesome. You're a step ahead of me. You got fast fingers again today. And checking to see if you're in here still. Awesome. So we do get 120 miles. Notice how we have inches over inches, so the inches actually divide each other out. We have miles left over. So let's look at page 32 and wrap this up with these other two examples. And these ones aren't set up for us. We have to figure out how to set them up. And so it says a house was assessed at $73,000 and has an annual property tax of $1,600. How much property tax would the owner of a house in the same neighborhood expect to pay if his house was assessed at $87,500? And what I'd like you to do is take a minute and set the problem up on your paper wherever you are before I set mine up. Take a second, set that up. And then I'll set mine up. Oh, don't show me. I don't want to see it yet. I just want you to look at yours and figure out if you have things in the right spots. So one way to do this is to put the tax on the top and the value on the bottom. So we have property 1, property 2. So property 1, tax is $1,600, value is $73,000. Property 2, we don't know the tax, but we know the property value is $87,500. So that's one way to set it up. Another way to set it up would be to have the tax over the other tax. Property 1, property 2, 73,087,500. So either of those will be fine, as long as the 1,600 and the 87,500 are across from each other, and then we're dividing by 73,000. And when we do that, we get $1,917.81. And usually with taxes, everything is rounded to the nearest dollar. Like if you ever do your taxes, everything rounds to the nearest dollar, so $1,918. And the last one, and after we do this, I'll see what questions you guys have and take the time to answer them. So here it says, Amy is taking 15 credit hours at Ivy Tech this semester and paid $1,997.25 for tuition. She is considering taking 11 credit hours in the summer. How much will her tuition be? And again, this is if each credit costs the same. So what I would do is I would just put the credits on the top. 15 costs $1,997.25. We want to know how much 11 credits cost. So cost is going across the bottom, credits are across the top. This is current, this is summer. And we're going to multiply 11 times 1,997.25 and then divide by the 15. So this is hours, dollars, hours, and we can see that we want to end up with dollars. And it looks like you all have the answer in there, $1,464.65. Beautifully done. You all are terrific. I love the fact that you get your answers in that chat box so quickly. Oh my gosh. Super job. Okay, so I'm going to actually stop the recording and then answer any questions you have. Don't forget that WebWork 3, actually the orientation, WebWork 1 and 2, and the discussion board are due tomorrow, Wednesday, January 23rd, and then WebWork 3 and Quiz 1 are due next Wednesday. I guess that would be January 30th.